Hey, geometry students, get ready for a lesson that is both easy and not so easy at the same time. Uh, there's kind of a lot to this lesson because we're talking about a new concept called the geometric mean. And the geometric mean itself probably isn't all that hard to understand. What makes it a little hard to understand is that we're going to be looking at triangles within triangles. Within triangles. No, just two. There's just two levels. But we're dealing with three different triangles that are formed, and two of those triangles are within another triangle. There's just a lot for your brain to keep track of. You ever see one of those puzzles where it's like, how many triangles do you see in this picture? And it's like there's a big triangle, and then there's some small triangles within that big triangle that you can make, and then there's even smaller triangles in those halfway small and it's just a lot. That's kind of what this lesson is. Be ready for it. Let's get started. We're going to start with theorem 51 before we define the geometric mean. So theorem 50-1, if the altitude is drawn to the hypotenuse of a right triangle, we'll pause. JKL is a right triangle. I'm going to draw an altitude from the hypotenuse. And when we have a right triangle and I draw the altitude in from the hypotenuse of a right triangle, that altitude is always going to be contained within the triangle. Remember, sometimes when we drew, like, for instance, obtuse triangles, the altitude would be outside the triangle. In this case, from the hypotenuse of a right triangle, the altitude is always internal inside the triangle. Notice that you see three triangles in this picture. The big one on the outside, JKL, small triangle, KML, and small triangle, JMK. The two triangles internally formed are similar to each other. So we have similar triangles, JMK and KML. And not only that, both of those small triangles that are similar to each other are similar to the big triangle. So we have three similar triangles formed. That is kind of amazing. Now, notice that in this one, it looks like JMK and KML are actually congruent to each other. They could be congruent to each other. Congruent triangles are also similar technically, but also look down below at the problems and see that we have triangles of all different shapes, and those internal triangles are similar to each other, and they're similar to the large triangle on the outside. All right, now let's define what the geometric mean is. We're going to define it algebraically, and then we're going to consider it in some geometric ways. The geometric mean for positive numbers a and b is the positive number x such that this proportion is true, okay? So we define the geometric mean using a proportion. A compared to x equals x compared to b. A to x equals x to b. Whatever that value of x is that makes that mathematical statement true, that value is the geometric mean. And I'm going to write that in a fancier way. We're just going to cross multiply. So another way to write the geometric mean is that x squared equals AB. We could also say that x, the geometric mean, equals the square root of a times b. The trick is sometimes just figuring out what a and b are. Sometimes we're going to be given the geometric mean, and either a or b, and we're going to have to figure out the other one. So we're going to be using these formulas here in this problem because that's the easiest way to solve the problems below. Now, we don't necessarily have to. Like, we could figure things out from the similarity statements and the triangles. We could figure things out from using Pythagorean theorem for some of these. But we're going to try our best to use the concept of geometric mean and the algebraic definition of it to solve some problems. Now, here's a couple of corollaries that are important when dealing with geometric mean. Notice these are going to start off the same way as theorem 50-1. If the altitude is drawn to the hypotenuse of a right triangle, then the length of the altitude is the geometric mean. The length of the altitude is x between the segments of the hypotenuse, between A and B. So the segments of the hypotenuse would be JM and ML, and the altitude itself is x. So this is the geometric mean of the hypotenuse segments, okay? The other corollary, this one's interesting too, and maybe even a little more complicated. If the altitude is drawn to the hypotenuse of a right triangle, then the length of a leg, I could choose this leg or this leg. It doesn't matter which leg I choose because we're going to deal with parts of the triangle corresponding to the leg I choose. So the length of a leg is the geometric mean. So JK would be the geometric mean of what? Of the hypotenuse, that's JL, and the segment of the hypotenuse that is closer to that leg. In this case, if I chose JK as my leg, JM is the segment close to the leg. So I can compare JL and JM. Now, that's a lot to take in. What we're going to be doing in the practice problems a lot of times is identifying which ones of these sections are like the leg that we're choosing, and then the segment of hypotenuse closest to the leg, or the altitude, and then one segment or the other segment. Okay, so just kind of keep in mind we have to be detectives and figure out how we can apply these corollaries to solve some of these problems.